All right, we're doing section 5, differentiability and cusps. Differentiability is the derivative continuous? So to test for differentiability, the first thing we're going to do is figure out if a function is continuous. If it's continuous, then all we have to do is check whether the derivative is also continuous. And so all we have to do is check for cusps. If the actual function is continuous, it still can have a point where, like here, the derivative is positive, say 1 going up, and then it switches instantly to negative 1. So if we drew a derivative graph here, like here's my graph, and it's like a negative 1, or starts at positive 1. Whoops. So starts at positive 1, boom, at this point it switches to negative 1. That's a step discontinuity. That's why this function isn't differentiable. So cusps are instantaneous changes in acceleration. As Mr. Buckley says, cusps don't exist in the real world. Even things like square waves, when I was an engineer, like boom, these are what square waves look like. They go up and then they go down. And so it's like 1, 0, 1, and actually they had spaces in between. It's like, but even these, if you zoomed in a bunch, so like if we zoomed in on this, it looked like it had a little tilt in it. So they don't exist in the real world, but in the theoretical world, they're really important to understanding how instantaneous changes work. Instantaneous changes are almost impossible to achieve in real life, which is why we ignore them in physics. So if we're looking at this problem here, if we had to choose where this instantaneously changes, because it's just like a man-made graph, it does have instantaneous changes in acceleration. We go from 0 here to positive, so that would be 1, and then 2, and 3, and 4. All of these spots, there's no curve there, it just kind of instantaneously changes. Now, when I gave this problem last year, and kind of the reason I'm not using it this year, is people said, hey, this is the real world. This is actual data. Cusps don't exist in the real world. And that's technically not an incorrect answer, so I kind of accepted that, but I don't really want to deal with that this year. So yeah, this thing, those are cusps in the sense of that picture, but if this was a real graph in the real world, those probably wouldn't be cusps. Whatever. Physics. All right, now to the harder problem, and kind of the reason I picked this problem in addition is we need to test whether or not this thing is differentiable. If you go back and watch my continuity video, I did a problem very similar to this. And so this is another one of those problems where we find values to make this thing actually match at the point. So our point is x equals 2. So we're going to have two different sets of two functions, or two equations, two unknowns, that sort of thing. So we plug in 2 into these, and we get 8c plus 2. And we need them to match, because for something to be differentiable, it also has to be continuous, so those values need to match. 8c plus 2 equals 6 minus d. All right, two equations, or one equation, two unknowns, no good. But we have the other information where the derivatives also need to match. So if we take the derivative, we get 3x squared c plus 1. And here we get 3x. And d is just a number. Both c and d are just constants. So the derivative of that is nothing. So if we had to write this equation, we'd say 3x squared c plus 1 equals 3x. Okay. What I forgot to do is plug in 2, because the derivative where we're testing for differentiability is at the same point. So we're actually going to get 12c plus 1 equals 6. And this is, there's only one unknown in this equation. We got rid of d when we took the derivative, which is good. So we're going to subtract 1 from both sides, and 5 equals 12c. And then divide by 12, and c equals 5/12. Hunky dory. All right. Now we just need to plug that back in and figure out what d is. And so we get 8 times 5/12 plus 2 equals 6 minus d. All right, 40/12. That's 3 1/3 plus 2 equals 6 minus d. This is 5 1/3 and subtract 6 from both sides, and we get negative 2/3 equals negative d, and so we get d equals 2/3. And so it's 2/3 and 5/12. Those are values that allow this to be both continuous and differentiable. Now, common problems people made in this section were, okay, not knowing how to get your two equations here, not realizing that one of the unknowns disappears when we take the derivative, and that's like sweet because it lets us solve for a value and just plug it back in. People were guessing values of c and d that worked and just finding one that works for this, but totally messed up this. And so there is like a strategy to go about this, and this is the strategy. Take the derivative and plug it in for the normal value and see where you can figure it out. Sometimes this won't go away in some of the problems, and so you have to do the two equations, two unknowns things where you like use elimination or substitution to get rid of one of the variables. This was a nicer version, and so be aware of that. Yeah, that's it for this section. Later.